But I want to just kind of more explicitly state this, and then we're going to use that to kind of build upon today, okay? So we're going to draw ourselves a picture of a yo-yo. So if you're a colored pens person, I'm getting out my pink pen to match my pink yo-yo. And you can do that, but again, you don't have to. So I'll unfreeze the screen in just a second, sorry. So there's my yo-yo. And I'm going to go ahead and put it on a string. And so this is like where my hand was as I'm whirling that yo-yo around, okay? And then I'm going to draw the trajectory or the path that my yo-yo takes as it goes around in that circle. This is not a perfect circle. I apologize for you perfect circle drawing people. If I ever told you about the math professor I had in college who was like double jointed, he was amazing. And this was like back before, smart boards and things. So he would like literally just, he'd start at one end of the room and he'd just use chalkboard the whole way. Like he'd just run back and forth. It was really adorable because he was like, shh. Anyway, but he was also double jointed. So he'd like put his elbow here and then go, and then he'd go the other way and he'd draw a perfect circle. That's some sort of weird talent. I guess, except they were all, same radius, but it was still kind of impressive. We're like, sure, that's amazing. Anyway, sorry, that was a digression for sure. All right, so we're going to just kind of draw. So the yo-yo's going around like this. Okay. And as it's going around, from the top-down perspective, the gravity force would be like going into the board. Does that make sense? And the floor force would be going out of the board. Those are kind of confusing. But there definitely is one force acting on the yo-yo that we can see. What's that force as the yo-yo's going around and around and around? The force of the string. And if I was going to draw an arrow for that force of the string, where would it go right now?
Out.
This way?
Opposite.
Is that what you're saying? I'm asking. Do you guys agree? If it was pulling this way, and I want to think this through because a lot of people like this, right? Want it to go this way. That means that it would be pulling out. But remember, where is this thing being pulled? It's being pulled in. Does that make sense? It's being pulled in. So that force of the string is actually just going to be along the string. So it's going to go in this direction. So the force of the string on the yo-yo. Now, just to be clear, and so that, if you get confused later and you need to look at this, this would be like the side view. So here's my yo-yo. Like kind of from the side view, like if you were sitting down like this with your head right along the floor. So here's the floor. We got the force of the earth on the yo-yo. And you've got the force of the floor on the yo-yo. And then you've got your string pulling in this way. So this is like my hand. I do not draw hands well, but for you guys, I'll try. There's my hand. This is the force of the string. It's pulling along the string. Does that kind of make sense? So this is the side view, and this is the top-down view. This is the one that we're really going to look at because it's more interesting. Okay. So as that yo-yo goes around and around and around, if Lily, the nefarious scissor-wielding Lily, decided to cut the string right here. Sorry, I'm not trying to imply that but I just I have to have some, person to assign that to, so I just picked you. I apologize if that has upset you.
No.
She cuts the string. Where's the yo-yo gonna go? What did we decide? Point with your pencil or point with your finger. Show me where it's gonna go. Tangential, right? It's gonna go this way. Does that make sense? Okay. And so we can talk about that. So I'm gonna draw an arrow this way. Is that a force? That arrow? Is there a force that way? No. This is just the velocity. Okay. And we did use a fancy word for that yesterday. We called it the tangential velocity. Okay. Tangential just means perpendicular. Okay. And the game is that whenever we have something moving in circular motion, okay, whenever we have something moving in circular motion, the velocity is always tangent or perpendicular to the radius. So I'm going to say tangential velocity. I'm just going to take that off. Say perpendicular to the radius. So again, if Lily cut the string, it's going to go this way. That's because if there was no string, there would be no net force. And an object with no net force is not going to accelerate. That means it's not going to speed up. It means it's not going to slow down. And it's also not going to change direction, right? Those three things are all true. Now, let's say that we have that string. It's just going to keep going. It's going to keep going. So the yo-yo wants to go in a straight line. What prevents it from going in a straight line? The string, doesn't it? The string says, no, don't go anywhere. Okay, so it goes right here, right? And now where's the tangential velocity? What? You with me there? So we could draw the string. And if it's the string, then we've got that's the radius. So then we can say, oh, there's the tangential velocity now. So for sure, it has changed direction, hasn't it? Now, if Lily cut the string here, it's going to go off at this angle. But thankfully for us, Lily has not found those scissors yet, right? So instead of going in a straight line, the string says, no, you can't go in a straight line. Okay, so here it goes. It's going to keep going. So now it's over here. You're saying, wow, this is going to be a really fun class, Miss Kay, because we're just going to keep going, do this the whole day. Indeed, we're not. I'm just going to do 3 of them just so you can kind of see what's happening. So in each of these cases, we're not speeding up or slowing down, but we for sure are changing direction. So we're not speeding up or slowing down. But because F net does not equal 0, we know we're accelerating, and the type of acceleration we're experiencing is a change in direction due to that force. Okay? Now, this is all very qualitative. It's just like talking about how things are happening. As you may guess, as physicists, we like to quantify things. We like to be able to measure things and understand them. So let's do that. Let's think about the tension on this string. So, Madeline, I'm going to pick on you for just a second because we were talking at some point in the last, day or two. You're like, I totally have seen this, not with water. I don't swing water around while I'm walking around town or whatever. But what is it that you swing around? She swings her purse around. Whee! Probably some of you guys have done that before with a purse or a bag or something like that. And all the random stuff that gets down at the bottom of your bag doesn't fall out. Same reason, right? Because of the same thing. Now, when you do that, you may notice that so that's your arm acting like the string, right? You may notice that it pulls harder or you have to apply a bigger force if you do certain things. For example, are you okay? Is everything good?
Yeah.
You can grab that if you need to, whatever you need to do. If we speed this spinning up, how does that affect the force or the tension force that's going to keep that thing in? Can you think about that? If you spin that faster, how do you think that's going to affect the force? What's that? It reduces the amount of force? What do you guys think? Does that make sense? So if you've ever swung anything, so if I swing it slow versus if I swing it fast, which one requires more tension? Fast? Does that make sense? Yeah. So we're going to try and quantify that force. So let's write that down. So if the velocity is bigger, the force required to keep it in a circle is bigger as well. So that's our tension force. Doesn't have to be tension. And next week we'll talk about other types of this, circular motion force. Okay. What else might we be able to change that might affect the tension on the string? The amount of force that's required. Yeah. The weight, like how big this thing is? Yeah. So I'm going to use just the mass, but that's pretty much the same thing, right? So if I increase, so let's say instead of using this little piece of plastic, let's say that I use a bowling ball. That's a pretty big change in mass. Which one's going to require more force, friends? This one or this one? The bowling ball, right? So if the mass goes up, the force required to keep this thing in a circle goes up as well. Anything else that you can think of that we might be able to define in terms of these circles? Yeah. The length of the string. Does that make sense? That's definitely going to change stuff. If the length of the string, which I'm going to call the radius of the circle, not because the length of the string is wrong, but just because sometimes we're not going to have a string. Maybe there's going to be something else that pulls or pushes, right? So the length of the string, which is really how big the circle is. If the length of the string gets bigger, how is that going to affect the tension in the string? So we're assuming the same speed. So if this thing has to move, so I'm going like this, right? Or like this, because it's the same speed. It's traveling over the same distance at the same time. Which one do you think is going to have a tighter string? This one? The smaller one, does that make sense? Versus the big one? Yeah. The smaller one is going to have a bigger tension. So as R gets bigger, what happens to F? It gets smaller. And those right there, that is the three pieces that you need to determine how big that force is. So we just figured it out. Yay for us. We're going to put it together. So a force that moves something, moves an object in circular motion. We never officially defined circular motion, but I'm guessing you can figure it out, right? Motion that makes something move in a circle. Well, it's going to be dependent. I'm going to build from the middle up. If the mass goes up, the force goes up. So that means it's got to be, as one goes up, the other goes up. As the velocity goes up, the force goes up. It's not actually a 1-to-1 ratio. Spoiler alert, I'm just going to tell you, but if you want to know why or you want me to go through it sometime with you, super happy to. The derivation is not hard, but I'm going to tell you that it's actually by the squared. So if the velocity goes up, the force goes up by the square of it. So it's going to go up a lot. Does that make sense? Okay. So it's not just like I double the velocity, I double the force. I double the velocity, I quadruple the force required. Okay. It goes up a lot. What about the radius? Is the radius just going to sit right over here? Do I multiply by radius? Or where does that radius go? What's that? I heard somebody say something. What'd you say?
I said we divide it
Why?
because it's inversely related.
Yeah, because it's inversely rated. As this one gets bigger, right? As the denominator gets bigger, then the whole number is going to get smaller. So we're going to divide by radius. Now, you could write this as a whole division problem here, but there's a reason I wrote it this way. So I'm going to leave it like that for now. But if you want to write a whole division sign there, you totally can. Okay? Moves object in a circular motion. F is equal to m times v squared over r. That's an important thing to know. Okay? I'm going to remind us, so that's the net force that's moving something in a circular motion. Okay? We have another expression for F net. It's one that we've been using for a long time, like since October. Do you remember what it was? It was simple. Two things multiplied together. What were those two things? F equals, anybody? It's been a while. MA. Does that sound familiar to you? F equals MA. So the reason that I wrote this one the way I did is because then you've got your M's lined up, and this thing right here, this gives us what we really want. This is what we came here for today. oops, new color. A, we call it A sub C. A lot of times people want that to be like the acceleration for circular motion. So if that helps you remember that, you totally can. There's actually a fancier word that it stands for. We've talked about it a little bit. We'll talk about it again in a second. Is equal to V squared over R. Sometimes we write a V sub T there to remind ourselves that that velocity is a tangential velocity. Come on. Just so that we've got this all labeled. R stands for what again? The radius of the circle. And A sub C is the acceleration of something going around in circular motion. Now here's the fun thing. We didn't expressly say this before. If we draw the forces in here, what do you notice about the pattern of the forces? Where is he pulling? Toward the center, right? All of the forces are pulling towards the center, which means that all of the accelerations are pulling toward the center. Not a coincidence. This is called centripetal, which means center seeking. Okay, it's a centripetal acceleration. Bless you. Okay, which means that every time that you have something moving in a circle, it's experiencing an acceleration. We know that because it's changing direction. And it's experiencing an acceleration that is always, always, always pointed toward the center of the circle. Does that make sense? Always, always, always pointed toward the center of the circle. If you have not put a big box around that yet, I want you to do that now. Because that's the big thing for the day right there. Okay. Questions right now? Are we okay? The next thing on my list is to try out some problems, just to kind of like play with this, make sure that algebraically we understand how to deal with this. We will get into some more deep ways to apply this, maybe at the end of the period or definitely next week. But right now, if you do not have a textbook that you can see in front of you, I'd like you to not literally run, walk safely back, get a textbook. You'll also need a calculator, and go ahead and pull your equation sheet out too, just so that you know where it is and you can look at it as we go here.
There's two forces that would interact, then going like with the string is just the one force. But if there's only one force, then not that you can see. When you do like the equations in like each direction, you did like
Yeah. Kind of. The thing that's different about this is that you've got a force that's actually pulling something in a circle, so it's in two dimensions. Do you know what I'm saying? So like when we have the yo-yo, so it's really three dimensions, which is kind of something. So it's very similar, and in a lot of ways, what you did before is going to help you for this, but it's a little different too. Does that make sense? That's a good question, though. Yeah. All right. So, friends, I'm going to let you know. Courtney just asked a really good question. I'm gonna kind of address it in a kind of bigger picture thing here. The problems that we do here are in a lot of ways similar to what we did earlier in the year. We're applying knowledge and we're applying what we've done to kind of get all of this in our heads. But because we haven't done this for a little while, sometimes it's a little bit intimidating to figure out how to deal with these kind of questions. So what I would like you to do as we're going through these problems is to really go back and use this step-by-step method, okay? Because I think it will help you, especially as we get into a little bit more complicated questions, help you to know what to do. I heard a lot of people say on the test that we just took, I just didn't even know where to start, what to do. And part of that, I think, is that we kind of have gotten out of the habit of starting from what we know. So let's turn to page 228, if you're not there already. We're going to take a look at practice question number 1 together. You have it in front of you. I'll read it out loud just so everybody is on the same page and write the same spot. It says a rope attaches a tire to an overhanging tree limb. A girl swinging on the tire has a centripetal acceleration of 3 meters per second squared. Says the length of the rope is 2.1 meters. What is the girl's tangential speed? A lot of things there. So let's start. Where's the best place to start on a problem, especially when you don't know? Let's do it. And when you're writing out your givens, you're not just going to randomly write numbers, but you're going to think about what they are. So take a look. And Josie, did you see at least one given in there that you'd like us to write down?
Yeah, the acceleration is 3.0
meters per second squared. And you said that it was an acceleration, right? Yeah. And so we can leave it like that because we know that we're in the chapter that we're in, because we know that we are in chapter whatever this is. I don't even know. You should probably know. Let me look. Is it 7? Yeah, there you go. Chapter 7. We are doing circular motion. We're doing centripetal acceleration. Because our equation sheet gets really long and scary sometimes, I'm going to go ahead and write this as A sub c so I don't forget, right? It says in there explicitly, we're doing centripetal acceleration. So I'm going to write that as A sub c. And if you have your equation sheet out, you'll notice that we are now at the very bottom box of that first column. We've made it to the bottom. That's impressive, you guys. We're all the way at the bottom now. That's cool. All right. Any other givens that we know? Cara, did you find any other givens?
The radius.
Yeah. How do you know it's the? I don't see anywhere that it says radius. How did you know it was the radius? You're exactly right.
I know because it says the length.
Yeah, that's awesome. I'm excited that you said it that way because that's exactly how it is. And I want to make sure everybody sees that. So I'm going to draw myself a little picture. So remember, sometimes pictures are helpful. You don't have to draw the picture, but sometimes it's helpful. So there's my tree branch. There's my rope. There's my tire swing. And I don't draw people, so I'm just going to draw a box. That's the little girl in the tire swing. Okay. And as she's going, so it's swinging, whee! And she's going that way. So she's like making this nice little curve that's kind of part of a circle, right? It says that the length of the swing is, I didn't actually look at the number. What is it? 2.1. But if we imagine that as part of a circle, Cara's exactly right. That is the radius of the circle. Yeah, yeah. So that's one of those things that you have to kind of process and you have to be willing to kind of be flexible on, right? So 2.1 meters is the length, which is also the radius in this case. Any other givens we have? What's our unknown? Yeah, it says, what is the tangential velocity, right? What is the tangential speed? So just kind of like with the centripetal acceleration, where we write A sub c, I'm going to write V sub t, again, just to kind of keep my brain in this circular motion business. That's what we're talking about. And then if you have it in front of you, your equation sheet has those three things labeled together in a nice little equation. A sub c is equal to vt squared over r. It's a new equation, a new day. Just want to make sure that everybody's feeling good about how to solve this. We're looking for v sub t, okay? So again, some of you are algebra whizzes and you've got that. You've already done it in your head and you know exactly what it's going to look like. But for those of us that are not feeling it, either just because it's Friday or because, algebra's scary, let's talk it through. How am I going to get rid of the r? Because I want v sub t. How am I going to get rid of the r? Multiply by r, right? Absolutely. Let's multiply by r on both sides. So the r's are going to cancel. So I've got r times a sub c is equal to vt squared. Do I want vt squared? What do I want? Just v sub t, right? How do I get it? Indeed. Undo a squared with a square root. So the equation that I'm going to write out is v sub t, that's the thing I want to know, is equal to the square root of r times a sub c. Now I can plug in my numbers. If you don't have a calculator out, I would strongly encourage you to get one out because I want to make sure that you know how to do this so that when you're working on your homework this weekend, you feel confident with it. Go ahead and plug it in. Once you plug it in, check with your neighbors and see if they agree with you. See if you guys have the same answer. How's it going? We doing okay? Okay.
What time?
And again, sometimes I feel like when we do stuff like this, it's just kind of like, you know, that whole plug and chug thing. We're going to dig in a little bit more on Monday and understand how this really affects more real life examples. I mean, maybe you're a tire swing aficionado and like tire swings are your thing. And so maybe this is something you know and love very well. We'll talk about some more of them on Monday too. What did you get for V sub t? Did you get a value? What'd you get, Grace? 2.51 meters per second. How'd we do? Do we agree with her? Cool. All right. Why don't you turn the page one over to page 230? We're going to look at question number 1 or problem number 1 there. It may look a little bit familiar. It's like the next step of that question. You're looking a little crabby. I can come over and help you if you want. Take a look at practice number 1 from 230. So this is like the next step in the problem. So it now says same rope hanging over the same tree limb, I'm assuming. Kid's still swinging on it. Has a tangential speed of 2.5. Fancy that, okay? It says now that the centripetal force is 88 newtons and it wants to know the girl's mass. Okay? So now we're using this. We're using the fact that the net force is equal to mass times centripetal acceleration. Okay? Centripetal acceleration leads to a centripetal force. Something pulling an object towards the center. All right? So just like we did before, start out with your givens. I'm going to go ahead and write stuff up here. But if you are ready to just go and fly with it, do it. That is awesome. But if you need a little guidance, then feel free to kind of follow along with me as I go through here. So it looks like the radius is still, so it's really the same problem, 2.1 meters. She's swinging with a tangential speed, V sub t, of 2.5 meters per second. It says that the centripetal force, so that's really the net force that she's experiencing as she's going in circular motion, okay, is equal to 88 newtons. And now we want to know the mass. All right. So on your equation sheet, the way that it's listed, it says A sub c is equal to VT squared over R. And it says that F sub c is equal to M times A sub c. So we got to put those two things together. Okay? Putting them together gives us what we had before, what we wrote down earlier that you guys figured out. So F sub c, the centripetal force, or the force that's keeping something in circular motion, is equal to M times VT squared over R. You can approach this one of two ways, and it just kind of depends on where you're at mathematically. You can just plug everything in here to find A sub c, then plug that in here and solve for M. That's absolutely fine. Like if that makes you happy and that makes sense to you, that's awesome. Or if you want to start from the big guy, that's fine too. Okay? If you do this one, I'm going to go ahead and do that more challenging one just to make sure we're all okay with that. I'm going to multiply by R on both sides. I'm going to divide by VT squared on both sides. And then the mess says that M is equal to R times F sub c divided by VT squared. So there's no square root that you have to do here, friends. That's what I wanted to make sure that you saw. Okay? The only thing you have to do is get M all by itself. So you're going to square that VT. Okay? But you don't have to do any square roots or anything like that. When you plug this into your calculator, make sure that you use enough parentheses. So you're not squaring the whole thing. You're only squaring the part that you really want to be squared. So it's going to be 2.1 meters times 88 newtons divided by 2.5 meters per second. And just that number, just that 2.5 is squared. Once you've got an answer, check with your table. See if they agree. Make sure that you know how to do this. The homework that you have for this weekend is problems just like this and like, kind of rearrangements of it. So I want to make sure that you understand how to do it. How'd we do? Did you get an answer, Jacob?
Yeah.
What'd you get?
29.53.
29.53. 29.53 what? We're measuring a mass. Indeed. And I didn't mean to put you on the spot in a mean way there, but a couple things here. You could just say, oh, I know that I'm measuring kilograms. That's good, and that's cool. If you want to kind of work through it, you can, and the units will come out to show kilograms, and that's totally fine as well. Okay? Questions on that? Are we feeling good? Cool. All right, so we've got a little bit of time, which is awesome, because that gives you a couple of minutes to get started on another problem. The 4 questions for homework, I'm just going to show you where they're at real quick. It's 2 more questions on 228, so those are centripetal acceleration questions. And then 2 questions on page 230, those are centripetal force questions. So I don't want you to put stuff away yet. I actually want you to get started on at least one of those, because you've got plenty of time to do that right now. The other thing that I'm going to let you know as you're kind of getting started and thinking about those is that if you were planning to do a retake from the test, I did finally get those review problems put back or put on to Canvas. So please take a look at them. I don't have solutions up yet, but I'll try and get those up like today if I can during 7. And know that I'll be ready for you to do a retake on Monday if you're ready to do it then. Okay? So go ahead and get started on this. Ask me questions if you have them. You've got a few minutes. Take advantage of it. Okay? Don't just put stuff away. Do some physics. 3 or 4 more minutes of physics. You guys have got this. Yeah, question?